Welcome to the course on power quality. Today we would like to discuss this topic of shunt active power filters. Coming to the outline of presentation, we would like to start from introduction, then state of art on shunt active filter, classification of shunt active filter, analysis and design of shunt active filter, principle of operation and control of shunt active filter, and modeling, simulation and performance of shunt active filter, then numerical examples, summary and references like. So, this is the outline of presentation. Now, coming to the objective of this, so first we will like to look into the requirement and application of shunt active power filter, then we will go to configuration of shunt active filters, we will discuss control of active filter, analysis design of active shunt filter and method of modeling and control of shunt active filter. So, coming with the introduction that current based power quality problems in distribution system, and the problem is related to power factor, the voltage regulation. Of course, these two cannot go together. Earlier also we discussed it, but either you can have compensation for power factor by providing reactive power, or you can have a voltage regulation. And then another problem in typically in current based power quality problem is like unbalanced current, like a negative sequence current. And then if you have a 4-wire system, you have excessive neutral current and then the harmonics current like also. So, these are current based power quality problems in the distribution system, and which causes like increased RMS current, increased losses in low voltage, low system efficiency, then poor power factor, poor utilization of distribution equipment, then heating of components of distribution system. Then the current based power quality problems in distribution further are derating of the distribution system, distortion in voltage waveform at point of common coupling, interference to communication system, disturbance to nearby consumers, and solution is a shunt active filter, which I would like to discuss in detail today. So, coming to state of art on shunt active power filters. So, now shunt active power filters are mature technology for providing harmonic current, compensation of reactive power, load balancing, neutral current compensation, and the shunt active power filter also used to regulate the terminal voltage, to suppress the voltage flicker, to improve the voltage balance in the 3-phase system. And of course, they are developed in varying configurations. Then with the there are advanced control strategy for them. Then the different solid state devices are used. There are a lot of improvement in that. Then improved sensor technology like Hall effect current sensor and voltage sensor for taking a feedback signal for the control. And then the microelectronics revolution has given a lot of microcontroller and DSP which are supposed to implement the control algorithm of these shunt active filters like. And these are like a typical like your Hall effect current sensor, and these are the kind of a DSP board how it look like, just to give example. And this is typically a industry made shunt active filter with the cabinet. Now, coming to the classification of shunt active power filter. So, we classified on the converter type, maybe current source converter we can use with the bridge structure, or we can use the voltage source converter. And in the topology we can have a like a half bridge topology or full bridge topology, and maybe or H bridge topology in case of like a 3-phase. Then the another classification is on the number of basis of phases. So, it can be 2-wire single phase system, or 3-wire 3-phase system, or 4-wire 3-phase system. Now, coming to the converter based classification. So, we can have a like a, you can call it current source converter for this shunt active filter. So, you have a nonlinear load, you have a supply system with the source impedance, you have a like a here the current source inverter and with the capacitor here. This inductor is typically not necessary, but you need the inductor on the typically on the DC side. That give you energy storage but you can understand what is the drawback of this current source. One is that this inductor is costly, bulky and noisy, and designing the inductor on DC inductor is not so easy. Another is that when two devices, because IGBT family or transistor family does not have a reverse voltage blocking capability, but in this case current source converter you have a negative voltage across it. To take care of negative voltage across the device, we use the series diode in series with that, but with the effect of this, when this switch conduct, you have a drop of both the devices. The losses of both the devices are there. Moreover, the shunt capacitor, because these are the PWM current, segment of DC link current, to make this current continuous, typically because switching frequency is quite high. So, this capacitor is mandatory, that is the additional components in case of current source. So, you have a more losses, higher cost, bulk in size, more number of component, that is the reason. Of course, people have initially used, you will find lot of attempts and research publication with the even experimental result, but later on with this people have gone with the voltage source type of your voltage source inverter fed active voltage source inverter kind of shunt active filter. So, here it is a in shunt filter you have a DC link capacitor which is electrolytic capacitor which is cheap, having a less losses, is smaller size, that is, and voltage source converter or inverter support with the IGBT in anti-parallel diode. So, it does not require a reverse voltage blocking ability. Moreover, when switch conduct, either your IGBT will conduct or diode will conduct. The losses of this either IGBT or diode are there. So, losses are also reduced here. Moreover, here do not need the shunt capacitor, you need the interfacing inductor, and in many situations this in place of interfacing inductor we might have a transformer for if you are using this shunt filter at different voltage at which this is injecting the compensation like. So, maybe that leakage inductance of transformer can also do the job of this interfacing inductance like. So, because of these reasons this had taken a lead into the technology and as well as development. So, now voltage fed or voltage source based voltage source converter based shunt filter are more popular like also. So, what is supposed to do? You want here sinusoidal current, okay. It draws harmonics and fundamental current. So, harmonics current should be met from here locally, only the fundamental current into the supply should give. Along with the harmonics current you can of course generate the reactive current or negative sequence current, but you have to certainly increase the rating of this shunt active filter. Some part we have already talked in DStatCom. There we are generating the reactive power as well as negative sequence current, but of course we were saying that we were not having the harmonics current here, but you can have here only harmonics for this filter because it is a filter, but you can have certainly even other compensation also like. So, topology based classification if we talk about, so we have a here now half bridge for shunt active filter using voltage source converter. You have a DC link, but the major drawback of this that this capacitor have a total current going through this. So, size of the capacitor or value of capacitor is very high and cannot be, because of this reason it cannot be scale up for large rating. But this is the bridge structure with the capacitor filter you can take to high rating. Virtually this bridge structure have a many benefit. You can use the unipolar switching. The whatever the ripple present here in the voltage, they will be of double the frequency at which you are switching the devices like. So, that is very specific benefit of this H bridge typically here, and this is your typically a shunt active filter with the bridge which is normally used in case of single phase like. And another features is that shunt active filter give absolute solution. It is not necessary you must have voltage distortion at the point of common coupling which we discuss in passive filter like also. So, coming to supply based classification, like a 2 wire means single phase. So, it is a current source converter, you have a DC link energy storage element, this is the bridge for devices which certainly give a pendulum current here segment of DC link current, and then of course, this is the capacitor along with this have to make a continuous current like also. So, that is the you can call current source converter based single phase active filter, and this is the voltage source active filter with the bridge, and you have a like a typically a ripple filter also sometime here with along with the capacitor. The small resistance is also there like which we discussed even earlier also in case of like a other converter circuit like So, this is voltage source converter which normally people use it, and this is 3 phase 3 wire voltage source converter with the active filter. So, you have a bridge 3 phase bridge, and you have a like interfacing inductor, then ripple filter and DC link like, and power control you maintain the DC link voltage constant also. So, it is supposed to ideally you because it is a filter you are supposed to generate only the harmonic, but certainly you can generate the reactive power also, you can generate the reactive your unbalanced current also from that, but the rating of the certainly rating of this your total converter as well as the inductor and other all element are supposed to be increased. The kV rating of the your converter, we will discuss with the numerical example how converter rating is increasing if you are providing the additional compensation. Then this is typically 3 phase 4 wire for neutral current compensation, the one topology, but it requires a large capacitor because entire neutral current this have to flow through these capacitor only. So, this is not too much recommended, but another topology with the 4 leg 3 legs for 3 phase compensation and 4th leg is 4th low. So, it provide the entire neutral current here locally and supply neutral current is made 0. So, this 4 leg compensation 4 wire this 4 leg compensation or 4 leg voltage source converter is quite popular with the self supporting DC link with the power control that we will discuss little later. And then or for 3 phase 4 wire you can use the 3 single phase H bridge. The benefit of this circuit that you have independent control and the switching frequency can be half I mean in these devices. Moreover, the DC link voltage also will be lower in this case, and that is the benefit of this, and it is a modular structure. So, you can have a edge bridge separately for each, and you can scale up to any voltage if you are putting already the transformer here. So, that is also, I mean, the industry prefer sometime this kind of topology for 3-phase 4-wire system. Now, these are the topology. Coming to principle of operation and control of this shunt active filter, and principle of operation of shunt active filter is typically the main objective is mitigation of current based power quality problems for harmonics. Mainly the harmonics filter is supposed to mainly compensate for harmonics, but if you want, you can have a reactive power also generate from this locally. You can generate the negative sequence current for compensation of unbalanced current. Then you can compensate even the neutral current also, whether it is because of the your harmonics. Even in the balanced load, you might have excessive neutral current, or you might have it typically because of the unbalanced like. So, it can do all the job, but you can understand once you really add these 3 more compensation, the rating of the your converter as well as, I mean, typically all elements have to increase. So, you require more features in control, the rating will increase, kVA rating of the your filter will increase, and certainly you can say cost will also increase like, but it can do that all those jobs. Then certainly it can mitigate up to voltage fluctuations also in fluctuating load like a furnaces or so, because you can probably mitigate the fluctuations by providing the major compensation which are source of the your fluctuating load, because it can even provide some energy storage too. So, the shunt filter results in sinusoidal balance current in the supply with this DC bus voltage regulation. That is the liability, I mean, with the control you have to meet, like otherwise you cannot have a pendulum control properly and control satisfactory like, I mean, also. And in general, a shunt active power filter has a voltage source converter connected to the DC bus, and AC side of it is connected in shunt, normally connected across the consumer load and across the PCC, point of common coupling voltage, and voltage source converter using pulse width modulation control. Therefore, it requires a small ripple filter to mitigate the switching ripple. It also requires Hall effect voltage sensor and current sensor for the feedback signal for implementing the control algorithm. So, what the controller or DSP use to implement control these, it check the feedback voltage and current, and typically do the calculation online and provide the gating signal for the devices of your voltage source converter which are working as a shunt active filter like. So, a DSP, digital signal processor, I mean, or the high level process like DSP is used in to implement the required control algorithm to generate the gating signal for the solid state devices of voltage source converter of shunt active filter, and the voltage source converter is normally controlled in pulse width modulation current control mode to inject the appropriate currents in the parallel to the parallel in the system, and they typically you can think about how it look like a kind of circuit. So, other requirement is like a DC bus capacitor. To sustain the DC bus, you require interfacing inductors, I mean, to between the your supply voltage and the pendulum voltage generated by the voltage source converter, and injection and isolation transformer. I mean, if you really you require isolation, and you require small passive filter for mitigating the point of common you can call it at the point of common coupling to improving the voltage profile. Otherwise, high frequency ripple will be there because you do not know the source impedance, but you cannot increase the inductance of the filter quite large. So, coming to like analysis and design of this shunt active filter. So, we have typical example of let us say of 3-phase 3-wire system with a 3-phase bridge. So, we have a here you can call it capacitor, we have devices, we have interfacing inductor, we have a ripple filter, I mean RFCF, I mean for deciding the compensation for your 3-phase loads. So, selection requirement is a DC bus capacitor and its voltage, an interfacing inductor, an injection and isolation transformer, and a small passive filter. So, coming to like a design parameters of APF is a 3-phase 415 volt 50 Hz with a source resistance of 0.04 ohm and source inductance of 1 millihenry is considered here, and a load is considered of 3-phase 3-wire rectifier used as a nonlinear load with a rectifier output of let us say output of 224.17 ampere, and RMS value of rectifier input current from this we calculated that is root 2 by 3, it comes 182.92 ampere. The fundamental component of current of rectifier input typically 0.779, it comes 174.78, and the harmonics current, I mean we calculate total harmonics current, it comes typically like your 55.86 ampere, and the rating of shunt filter now will be 3 VFC IF. So, you have a 3 times than the phase voltage, the phase current. So, it comes typically order of 50.19 kVA, and you can round off to 50 kVA like or so. So, coming to like a shunt filter rating of 50 kVA, the shunt filter voltage rating will be 415, the shunt filter current rating will be 69.82 ampere, and the available voltage ripple at the DC link permitted 5%, and the allowable shunt filter current ripple 10%, which comes around 6.983 ampere. So, you can have a DC link voltage calculation. This is standard formula for 3-phase voltage source inverter or converter, 2 root 2 VL upon divided by M, and if you put the like M equal to 1 and the value, it comes 677.692, and here M is taken a modulation index 1, and thus the VDC of this 677 for 415 volt distribution system, and it is selected to 700 volt like also. So, coming to selection of DC bus capacitor from this energy balance equation, what is this minimum voltage permitted, this is nominal voltage, and this is the typically the how much you can have a active power flowing into the typically into the AC side of the. So, putting the all the value, we get the capacitor value typically 7564 microfarad, and here VDC the nominal DC voltage, VDC1 is the minimal voltage level of the DC bus, and A is the overloading factor, and T is the time for which the DC bus capacitor voltage is to be recovered, and thus the calculated value of this 7564, and you can select 7000 next available value of 7600 microfarad. So, coming to the selection, another criteria of selection of capacitor, because you might be having like a load unbalance. So, for that you say second harmonics also comes on the capacitor. So, based on this criteria, if you take calculate all those, so it comes around 3260.421, and I0 is the capacitor current, and omega is the angular and VDC is the ripple voltage. So, capacitor obtained is 3572. Thus, the highest between the two values selected, that is 7600 microfarad like. And coming to interfacing inductor, that is the formula for inductance between the inverter root 3 amp VDC upon 12 AFI ripple current in the converter, and putting the value like all the value here, so it comes 1.206 millihenry, and here modulation index and A is the overloading factor, and considering the ripple current of 10%, switching frequency of 10 kilohertz, M equal to 1, VDC 700 volt for 415 AC, and A equal to 1.2. So, LR calculated from here 1.206, and thus we can select the value of 1.5 millihenry for this. So, selection of a like a ripple filter to filter out the noise from the voltage at PCC, the time constant is RF CF must be much lesser than your time period for corresponding to switching frequency, and which we consider normally 1/10. RF is the ripple filter resistance, CF is the ripple filter capacitance, and TS is the switching time, and ripple filter impedance corresponding to for a particular frequency will be ZF under RF square plus 1 upon omega C square, where omega is the frequency in radian per second, and you can find out the impedance of this ripple filter corresponding to 50 hertz if you are taking a 10 ohm resistance and capacitance of 5.5 microfarad. So, it comes 578.832 ohm, and for switching frequency of let us say TP even a 1.8 kilohertz, if you put this it comes only 10.41. But if you really are calculating, let us say you are operating for shunt active filter 10 kilohertz, then it will moving for typically or it will remain only order of 10 ohm, because resistance is taken 10 ohm. You can select the 5 ohm also, that will reduce to 5 ohm. But now current you can consider for fundamental, considering the switching frequency equal to 10, ripple filter parameters are selected 10 ohm and 5.5 microfarad. So, the impedance offered for a switching frequency is 10.41 ohm, and its which will certainly take all the higher switching harmonics into it, and impedance offered at fundamental frequency is 578.83, which is sufficiently large, hence the ripple filter draws negligible fundamental frequency current, and the losses in ripple filter will be equal to PLF equal to 3 I square RF, and I is VSP upon Z. Losses at 50 hertz, you can find out 50 hertz frequency, 50 hertz impedance at 50 hertz of this ripple filter, and current will be corresponding to 0.414 ohm, and the losses in all three phases 3 into this current square into 10 ohm, it comes only 5.14 watt irrespective of the rating. So, that much the only loss in this ripple filter like. And coming to the voltage rating, selection of voltage rating of solid state devices, we take a DC link voltage the highest, then we take a typically 10% overshoot may happen. So, with the 10% overshoot under dynamic condition, so we can put the value of 10%, so it comes 770 volt, and with the typical calculated value and with the appropriate safety factor, normally we consider 1200 volt IGBT for this voltage source converter in working in shunt active filter. And switching frequency of typically of we take a the switch current 1.25 times the ripple current plus your current flowing into the passive filter. So, if we calculate like a 10% and this is the current into the filter, then we can have the total current of the your switch corresponding to that, and that is calculated, and with the safety factor of this we normally select 300 ampere. So, it is a 1200 volt 300 ampere switch are calculated. Now, coming to the another case, design of 3 phase 4 wire active filter. So, we take another one leg here for fourth leg, and the supply here consider 3 phase for 1550 hertz with a source resistance of 0.0 ohm and source inductance of 1 millihenry, and the load is consist of 3 single phase rectifiers with resistance of 2.5 ohm and inductance of 25 millihenry is considered as a non-linear load, and its rectifier output is your ID equal to 86.28 ampere, and RMS value of the rectifier input current will be your typically your same as the 86.28 ampere, and RMS value of rectifier fundamental RMS will be your 0.9 times. So, that is typically your 77.65 ampere, and the RMS value of harmonic current will be your RMS minus fundamental current, that is 37.61. The your APF neutral current will be the same as the load current, so that is 37.61. Since there is it has to cancel the total load neutral current, and the V rating of the passive filter 3 into IF into VF. So, this will be like your 36.096 kVA, and the volt typically rating of shunt filter will be 1.25 for extra dynamic. So, it comes 45 kVA or so. And selection of DC link voltage, say by 2 root 2 into by 3, so it comes 67.69, and here I am taken a modulation index 1 and DC link voltage calculated 677.69 for 15 volt, and we select 700 volt like. And the capacitor value from this dynamic equation, putting all the value, we get the 5092.76 microfarad, and we select the next value order of typically order of 5500 microfarad like. And the DC link capacitor another relation corresponding to second harmonics, that comes typically 2923, which is much lower than the previous value. So, we select only then 5500, which require for energy balanced one like and the interfacing inductance from this relation we can put the value and we get 2.239, and we select typically around 2.5 millihenry inductance like and the fourth leg, that is the neutral, this is the formula for that, and putting the value we get 2.985 millihenry for the neutral conductor like. So, the ripple current allows the in the ripple neutral current, and this is calculated this. So, we select the 3 millihenry corresponding to that like. And selection of ripple filter to filter out the noise from the voltage at PCC, the time constant is let us say much lower than time constant filter than the switching frequency. So, it is around consider 110, where RF is the ripple filter resistance, filter capacitance, TH is switching frequency, and the impedance of this corresponding to frequency will be your RA square 1 upon omega C square, omega is the frequency. So, for fundamental frequency it comes 578.82, and for switching frequency it comes 10 typically your 10.41 for 10 kilohertz here like and the considering switching frequency equal to 10 kilohertz, the ripple filter parameter are selected 10 ohm and 5.5 microfarad, and the impedance corresponding to switching frequency comes 10.41 ohm, and for fundamental frequency it comes 578.83 ohm, which is sufficiently large, hence the ripple filter dodge the negligible current. And losses in ripple filter you can find out typically from this relation 3I square RF, and for the losses we calculate the impedance. The current will be your phase voltage divided by the impedance. So, this your fundamental current is only 0.414 in ripple filter, and the losses will be only 5.14, 3I square R only 5.14 like also. If you take a 5 ohm resistance, it will be further lower value of this, because that fundamental impedance will be order of the same like. And coming to selection of voltage rating of solid state devices, so it is a solid state device comes DC link voltage, that is the highest voltage plus overshoot, and considering the 10% overshoot it comes 770 volt, and then we select with the safety factor 1200 volt devices. Coming to current rating 1.25 times current ripple, and putting the value of this, it comes 71.188 ohm ampere, and then with the safety factor we select 200 ampere corresponding to the IGBT of that.